Good afternoon. Thank you for showing up for the deep learning presentation. This is deep learning going beyond machine learning. Are you guys in the right room? Thank you. So I'm Chida. That's an easy name to call me. And this is Vishal. Both of us work for a cloud solution provider called Day One Solution near Washington, D.C. area. So we picked up the topic, even though it's a sponsored session topic, a topic which can be of interest in the future, the upcoming topic, deep learning, which is going beyond machine learning. So what we're going to expect from this session is we will talk about what are the data analytics options on AWS, which you all heard in every session, which we'll throw a slide for you. Machine learning, what does it mean at the high level? Then talk about Amazon machine learning, then some sample use cases. Then we'll get to the real meat called deep learning, which goes beyond machine learning and who's using it, how it's being used. Then we'll get you some sample use cases. Then what is Amazon providing for the deep learning beyond the machine learning? We should talk about it and any question and answers. So the data analytics options in Amazon, this is, as you all know, this is as of yesterday. So today NDJC announced so many other services today. So this basically, there are three levels of, three phases of any data analytics. One is ingest the data, then store the data, and then beyond that you analyze the data. So these are all the products which we use, which we heard about, all the Amazon Kinesis, DynamoDB on storage, or S3 is a common storage option, RDS, whichever way you use it. And how does the Redshift work? Redshift also can be used for analyze. Amazon EMR, which is their popular Hadoop option. Then there is also Kinesis has got the other option of consumer consuming it. And the last but not the least is machine learning that they released probably 4 or 5 months back. What we will drill down is we will be a little light on Amazon option because you are overloaded with a lot of Amazon buzzwords. So we will talk something about machine learning, right? So what is machine learning? How many of us know about machine learning? Simple example. How does a child just start recognizing things, differentiate between Bruce Willis and Jason Statham? How does a child recognize these images? Either somebody teaches them, or they look at a movie, or they look at a picture, and they start memorizing that, okay, this means this person. It's talking about recognizing who is his or her mom or dad. So this is basically how do you teach a machine to learn things from the beginning. That's what the fundamental of the machine learning. To get to the machine learning, on the technology side, it uses all of these features, all of these components, all of these inputs, all of these come together. Artificial intelligence, then information theory, what are the information available? Neuroscience and neural networks is basically, neural networks is basically translation of an equation, mostly the mathematical calculation. How do you optimize and control the information which you just learned? And beyond that, the statistical modeling. All of them are number-based, a lot of numbers. How do you derive an image into a number, into an equation, and start feeding a machine to start learning about it? So, Vishal will take it from here.
Okay, so, well, we heard a lot of heavy terminologies, artificial intelligence, neuroscience, statistical modeling, and it seems like pretty heavy session. But actually, you'd be surprised at how often we use machine learning techniques on a regular basis. With the advent of smartphones and getting high megapixel cameras on these small devices, everybody has turned into a photographer. But if you've used any photo management application, you know that they come with face detection technology, right? That's part of machine learning. And then from face detection technology, it can categorize these photos into groups based on the faces that it recognized. But then, you as a human being, we still have to train the application as to who those faces belong to, what the machine is seeing, how to interpret that. That's teaching the machines on how to interpret the data that it has analyzed. So for example, over here, you can see that you can tag the first image as an image of a bear, second image as the image of an eagle, and the next time you feed similar images into that application, it'll be able to automatically determine and categorize those images. Same way, third image, when your machine analyzes that image, it will detect there are people in that image, but then you'll have to teach who those people are, right? So basically what it is, what is machine learning? It is using the machines to discover trends and patterns in the data. It is using the machines to compute a prediction model based on the data that it is seeing that has been recorded in the past. So machine learning can provide you with insights into a probabilistic future, an outcome that can happen in the future based on the trends and patterns that it sees in the data as observed in the past. So this is the difference between a traditional business analysis and machine learning, where traditional business analysis focuses on the past data and just records what has happened. Your machine learning process takes that data and tries to come up with a way to predict what can be the possible outcome in the future and what the probability can be. Now, having said that, you can train the machines either in a supervised manner or in an unsupervised manner. The place where you do supervised learning for machines is the application that we've been talking about, the photo tagging and photo recognition. So once the machine identifies the edges and the people in the photo, then you train the machine as to who those faces belong to. If you think about unsupervised learning, that would be more like categorization of raw documents that you may have in your content management system or in your email archives. Looking at the document corpus itself, coming up with the domain of topics covered in your archives or domain of topics covered in your content management system, and then categorizing those documents into these groups. So that is where you will get more of unsupervised learning, where the machines themselves try to come up with the relevant domains, looking at the content of the document themselves, and then do a further analysis on the entire corpus to classify based on the domains extracted. The process, it's pretty simple. You start with training the machine with data for which you already know the answers. For example, in the first pass, you have a set of photos. You would tag those photos for what they are, like my photo versus Chida's photo, and then you would train the machine that who these people are in the photos. Once you get that training data, you use that to build your machine learning models, where a machine learning model is nothing but a mathematical computation formula which tries to take that data and match it with a corresponding outcome. Now, once your model is generated, the next step in machine learning process is validating the outcome of your model, where you again take the data for which you already know the answers, but this time, let the machine predict the answers and compare it with the known values, the truth. And if the predictions produced by your machine learning process is within an acceptable range of acceptance, then you take that model as a final model for use with untested data, all right? But if your predictions are incorrect, grossly incorrect, then you come back, update your model, change your parameters for coming up with those formula, and then run the process again. So that's the typical machine learning process. And in all this process, what's important is selecting the right criteria of input that I have to supply to my machine learning algorithm in order for it to come up with the right answers that I'm looking for. what are my predictions going to be based on? How do I select the input features? In terms of photo, should I select the background colors and images? How important would that be versus the edges or the pixel hue contour distributions? That becomes critical. So feature engineering in machine learning is critical. The second thing that is critical is figuring out the target, the end value that I want to predict, that I want the machines to come up with. And third is the function that I'm going to use to get to my outcome. The function can be a simple classification function, it can be a regression function, or it can be a dimensionality reduction or a cost reduction function. So in order to get that, what machine learning process does is it takes the data that you have and converts it into some kind of a mathematical representation. Predominantly for images, it can be vectors of pixel densities, colors per pixel, the edges and contours, so on and so forth. And then, based on these feature set and what you select as the criteria for prediction, it'll try to run one of your algorithms for doing predictions, either, like I said, classification or a regression or a cost reduction function. And then it'll come up with the target answer, right? So basically, here's something that's very critical in machine learning. It is, like I've said, the feature engineering, selection of input features. Let's go back to the example of Bruce Willis, identifying Bruce Willis, right? If my input feature in layman term is, okay, Bruce Willis is a person who's bald and wears a black suit, and that's my input feature for the mathematical model for the machines to learn who Bruce Willis is. With that input feature, if I supply an image of Jason Statham, chances are the machine will tag Jason Statham as Bruce Willis. Not the fault of the machine, it is fault of the trainer who's training the machine because the input selections are inadequate. This situation is called underfitting. There's the other side of that, which is called overfitting, where you select too many input features which may not be relevant to the output that you're looking at, right? So machine learning process relies heavily on this feature engineering, striking the right balance between underfitting and overfitting of your selection criteria. So to summarize again the entire process, you start with the data for which you already know the answer. You use that data to create the model and then to train the model for machines to learn. You identify the target. That target in this case is the value that you want to predict. It can be a simple Boolean variable like whether the customer is going to buy my product or not. Or it can be a probability distribution of a document belonging to a certain set of topics that I'm trying to classify the documents as. Once these two sets are identified, you then train the ML model based on these features that you selected. If the results is in below a certain threshold of acceptance, you go back and tweak these input selection criteria. Or you go back and tweak the cost functions that you're using for coming up with the answers. Once you are satisfied with the results of the ML on the training data, then you use that model for getting your predictions on untested data for which the answers are not known. So all this sounds fancy, but when is the right time for me to pick machine learning for doing predictions and for coming up with the values that I'm seeking? Well, if what I want can be categorized or summarized in a simple if-then-else rules engine structure, if JBoss rules or some kind of rule engine can suffice my predictions, probably I don't need to go all the way to machine learning. But if my data has a lot of variance in, like it's an image data or a video data feed or an audio data feed, which I cannot simply categorize with a regular if-then-else structure, or if scalability is an issue with respect to using the classifications, then machine learning might be a good fit for it. Now, if you decide to use machine learning for coming up with the prediction and analyzing your data, Amazon is a good friend of yours because they recently released machine learning as a service. And Chira, you can take on.
So let's talk about the Amazon machine learning, what Vishal talked about. I liked when he say, it's nothing but, but I think there's a lot of things it's doing, right? So the Amazon machine learning is actually a service available by Amazon. Actually, it's just 3-click process. You load the data, then you pick the model, then you look at the outcome, then you validate the outcome. It's just a 3-step process which created by Amazon machine learning. So basically, it covers 3 type of machine learning algorithms. So Amazon, based on their, because they use machine learning on their Amazon.com, as you all know. So they pick the top 3 type of regressions, the type of models which can be used in any machine learning process. The one is the binary classification, whether the customer will buy this or not. Then the second one is multi-class classification, right? There are multiple kind of output produced, like a lot of categories for a blog. That's the learning process. Then the third one is the regression, meaning prediction, whether based on what happened in the past, what is the percentage of cheetah watch this movie or buy this product. So those are the 3 machine learning algorithms which Amazon thought covers a wide range of application which we can use. So they just give you that 3 options. So basically, the process is 3-step process. Initially, we load a sample data set. The way how it works is, for example, I'll try to be dumbing down how it is happening. Let's say you pick a spreadsheet of 100 columns, and your 100th column is your output, what you have observed in the past, saying that 99 columns are the attributes, what he was talking about, the feature engineering. So based on the 99 attributes for a particular behavior, the outcome is the person bought or the person did not buy. That's your 100th column, right? So you feed that into the machine learning, comma-separated file, or S3, or Redshift, which you talk, which those are the inputs. So what machine learning does is it picks 70% of that. Let's say it has got 100 rows in it. So it picks 70% of the rows to do a self-learning of machine learning. Amazon knows by looking at the result column which one of the algorithms to use, either regression or the binary or the multi-classification. So then it comes back and produces the outcome, what Amazon thinks the outcome should be. Then you validate it, this is true or false. Manual validation, which is kind of supervised learning. So you are supervising, saying that yes, Cheetah in the past, if he has got all this demographic information, and Cheetah has the potential chance of buying this. So you validate manually, then that'll become a model for that machine learning from Amazon. So when you feed the next 1,000 rows into this, so Amazon will come back and fill you that, the machine learning will come back and fill you the 100th column, what really happened to that. While you are validating the model, you yourself says, out of 100 rows, what Amazon predicted or what the machine learning predicted is 70% or 80%. You want to increase the number of percentage so the model gets refined. So that's basically the background of how the Amazon machine learning product works. So you can upload that data from either S3 or from Redshift to feed into the machine learning. So like I said, these are just 3 screenshots they have, and it's basically they let the machine learning decide what algorithms to use to give you the output, right? So why this is very popular, it is called pre-built machine learning algorithms. It is coming out of what they have learned from the retail, what they have learned from the prediction which they have done, and that's what they're giving it. It has got a very tight integration of Amazon AWS ecosystem. It has got both batch and real time. The real time, if you want to use real time, you feed into the Redshift, and the model keeps changing it. Then the models are created very fast, actually, because once you put the input data, the models are created very fast. Then they have some data visualization and exploration of how much data you ingested into this machine learning and what it is predicted. They have come in-built products. The data transformation, they do some level of data transformation, but you might have to prepare your data, the 100 column, 100 row spreadsheet, probably you might have to prepare what you're looking for the future engineering, what Vishal was talking about. Of course, the last two are their mantra, fully managed, pay as you go. That's the Amazon machine learning. Now, what are all the use cases? Obviously, the prediction or the classification or grouping. So the prediction is whether he will buy or not, or what is the chance of him buying or clicking the video which I'm recommending. The classification is basically tagging a bunch of images, or what kind of, like we all know Netflix has got 20,000 categories of movies depending upon what is happening in the movies. Then auto-categorization in the text based on the predefined data. Now, these are some of the use cases. Personalization, if you look at LinkedIn, it is so much personalized. Before the first page is thrown to you, there's so much thing is happening, what is they are throwing at you. It's a personalization. What you're looking for. Netflix is very similar. I try to avoid the Netflix because you hear Netflix a lot in the conference. The document classification, how do you auto-classify the documents when you find out this is a model? Automatically, when you ingest a new document, it can auto-classify it. The blogs are a very good example. One of the use cases which we are seeing on a real world is dead SharePoint sites of millions of documents. They don't know what does it mean. So you can take that model, you can take that 500,000 document or 1,000,000 document of several content management solutions and feed into a machine learning algorithm which will give you auto-categorization of probably these are all the things are there based on the machine learning what we learned about the text. Now you do a supervised learning of, yes, this is correct, this is not correct. You decide to choose to delete or keep it. We are seeing a lot of old documents in the oil industry where the documents were created manually long time back. So they are trying to classify them, how to group them. Fraud detection just works on the other side. It detects the anomalies, while the other one detects a pattern. This detects the anomalies. So then it can be flagged as fraudulent. Recommendation engine, obviously, Chida watched this movie and he would potentially watch. The recommendation engine is a very common use case in the machine learning. And Amazon machine learning, the tool, what the services they give is much more powerful just to cater some of the smaller prediction recommendation engines. The customer churn prediction based on now what is happening is Chida is coming to my site, but I don't think he's going to buy. Can I now, what I can do for him? So you predict that I'm slowly dying. My site is slowly dying. How can I make him buy it? So these are the very common machine learning use cases. There are several machine learning use cases which you will find out. Now, I'm going back. Now, so we talked about machine learning. Now Vishal will take you to the real content of this presentation. What is deep learning?
So, time for some confusion again. If you're not already confused about machine learning, then be prepared. Because deep learning is nothing but an extension of what we've been talking about. In traditional aspect, machine learning aspect, where focus is on feature engineering, striking a right balance between selecting my input features for the outcome that I want. Deep learning, on the other hand, tries to do that on its own. What it tries to do is, given a data set, it will try to break it down into its, every data, it will try to break it down into an atomic level. In case of images, it is multiple layers of information, each representing one aspect of that image. One set of layer would be the mathematical difference between all the pixels that you see in the image with respect to the pixel densities. Another aspect, another layer of that same image would be the hue saturation levels of each pixel, and so on and so forth. And what deep learning process does is, it tries to apply the same machine learning principles to each of these layers independently, feeding the outcome of every analysis to a next set of analysis or regression that you can say in some form of what we call a neural network. A neural network is basically nothing but, you can think of a neural network as a composition of small mathematical functions, statistical functions that operate on some level of mathematical representation of your data and then feed it to the next level of analysis. It's all interconnected either in one direction, which is called feed-forward neural network, or you can have a feedback loop on your entire network with backpropagation, where using the feedback, the deep learning process tries to optimize what it has learned. So basically in deep learning right now, where in traditional machine learning, we would be selecting the criteria, the feature set ourselves to come up with the outcome. Deep learning works on an entire end-to-end basis, breaking down your data into multiple layers of representation, and then working through these same mathematical computations in parallel in some form of a network graph, all right? So the objective of deep learning, if you look at it, go back to the same examples of the images that we saw, where machine learning tries to just identify the edges and try to detect objects in the pictures. With deep learning, the focus is on trying to get the context of what it is seeing. Not just identifying the object, but also identifying what that object might be probably doing. This is particularly useful when you're analyzing huge feeds of audio or video data. With image data, for example, in this scenario, if I ask you, look at the third picture, and what do you think the people that the machine has identified in the third picture, what do you think they are doing? You would say, they're playing, they're having fun, right? Now, why would you say that? Because there's another object in that picture, which is a ball. I don't know how much it is visible, but you would see a ball, and you know from your past experience as a kid, as you grew up, you use the ball to play and have fun with. How would you translate that kind of analysis? How would you make the machines deduce or infer that the people in the third picture are having fun? How do you categorize that? That kind of inference and analysis is useful, particularly in terms of in defense projects, where you're observing a lot of satellite data, images taken from the satellites, and you're trying to find which images represent a potential threat or a danger. How does a machine flag a particular set of pictures as a potential threat, right? So that is where deep learning heads towards. And like I said, deep learning, in order to build such inferences, in order to come up with such analysis, it uses something called as neural networks, where a neural network is nothing but a collection of, in biological terms, if we talk about it, it's a collection of neurons communicating with each other. In machine language terms, we talk about it, a neuron can be treated as a mathematical function which gets an input data and produces an output, and that output is then fed to the next set of neuron or the next set in the neural network. And that is, in very layman terms, what deep learning uses to come up with analysis without you having to specify to the network or the program what features you are going to use to predict the outcome. Now, there are different kinds of neural networks that are used, and that becomes the critical factor of your deep learning process, is creating the neural networks, the kind of neural network that you would like to use, a feed-forward or a neural network with a backpropagation, feedback analysis, and all those things. The process is pretty much similar to what we've been talking about in machine learning. You start with a set of data that you already know the answers for. And using that set of data, without specifying, in this case, any input for it to come up with the output, you feed it to the mathematical model. In terms of classification, what you do is the data that you have would already be categorized and auto-classified, and you would know what classification these data belong to. And then you would feed it to the neural network. And what the deep learning process will try to do is, it'll try to kind of reduce the cost or the error rate between what it sees and predicts and what the final actual outcome is. And that error is fed back into the neural network to fine-tune itself. So basically, if you ask me what kind of mathematical functions would it be, a neuron is nothing but a function, mathematical function, which has a cost association and a weight attached to it. And these parameters are the parameters that the machine will try to tune and fine-tune based on the feedback or the variance that it sees in the observed outcome and the actual outcome. And that's the self-learning process that the machine uses to come up with the answers in a faster manner and in a more efficient manner. So if you look at the previous slide, you can tell that the machine identified a panda as a bear, and then you fed it back into the neural network to correct itself. That feedback is nothing but the variance of the prediction to the actual value, again represented in some mathematical format. And then what it does is it takes that negative feedback into account and converts the cost factor or the weightage that it has used in its computation to come up with the correct analysis. So finally, at the end result of that is once your neural network is trained with enough input data that you use for training, it becomes robust enough to come up with very good predictions. So the process between traditional machine learning and deep learning is slightly different. Here, the focus is on coming up with the right set of functions that you would use in your artificial intelligence or neural network program. And then training that neural network to be robust against any variations that you can throw at it in terms of the data that you throw at it. That is where the critical part of deep learning focuses on. Once you train your network, you can use the same network to analyze the various types of data as long as the data can be represented in the same set of mathematical representations. Once your network is trained and you're happy with it, then you deploy the network for automatic feedbacks and classifications and self-learning. Then once your network is trained enough, the process becomes semi-automated or fully automated. Again, for deep learning, one of the critical elements is the process itself takes the data that you have and breaks it down into atomic layers, where each layer can be worked on independently by these neural networks. In terms of images, it can be vectors of pixel densities, motifs, parts, contours, edges, all of these taken together, each one layer at a time. What the deep learning process will do is it will try to use these low-level features to come up with the higher-level hierarchical feature set. So from vectors of pixels, and motifs, and all these data together, it will try to construct what it is supposed to see at the end. Same thing with videos. Videos is interesting because videos is nothing but a collection of images taken in a sequence. So every frame is broken down as an independent image, and every image is further broken down into its own atomic structure, like what we've discussed about, vectors of pixels, motifs, parts, contours, etc. Text is broken down into characters, words, clauses, sentences, and then collectively it's used to analyze and come up with the domain and context, which are higher level features based from the atomic representations. Speech is interesting too, and a lot of deep learning research is going on in speech recognition, where your speech patterns is broken down into audio, band, frequencies, wavelengths, modulations, tonality, and phonetics, in order for machines to predict what you're trying to tell it. Because in speech recognition, what happens is my way of talking is different than Chida's way of talking. So when I say something and when Chida says the same thing, the machine needs to understand that these two are talking about the same context. It's not different. It's not a foreign language that I'm speaking when you compare it with what Chida says, right? So with that, I'll let Chida talk about the advantages of deep learning.
So just to, for the sake of the time, try to run it. So the features, basically they're automatically deduced on the deep learning. Like you saw that a picture can be deduced with so many other features within the picture. The robustness to variation is like a contradictory statement, but when things vary, machine learning, will be more robust because it'll detect it faster. That's how it learns. Then you can reuse in several applications. And the massively parallel computation, actually, the answer to this is how the GPUs are working to resolve you have to make the decision much quicker on the deep learning than the machine learning. So what is the traction in the machine learning? Today, as you heard from Andy Jassy today, is people are talking about petabytes, zettabytes. Now, it is not just storing the data, how fast you can process it, and how you can make value out of it. So the cloud and the big data ecosystem, the evolvement of that in the past 6 years is really making leapfrogging in the deep learning algorithm improvements also. Like, there are a lot of advancements have happened in the better GPU, which we'll talk about what GPU versus CPU is. And the advancements in the GPU acceleration on the machines is actually make this processor much faster. Now, what Amazon is providing on the GPU side, I think they have a class of server types called G2, which is basically doing the CUDA processing. That the CUDA is actually an API coming out of NVIDIA to make use of the GPU processing power, right? So, for example, the 4 NVIDIA GPU process actually will give you like 1,536 CUDA cores, which we will see in a little video how these two different. Now, do you want to run the video now? Now, we wanted to show you a quick video. What is how this GPU versus the CPU is. So basically, CPU is a serial processing, and the GPU is taking that into a parallel processing. As he talks about mathematical calculation, the mathematical calculation can be run much faster on the GPU because it can be parallel processed, right? So let's have a quick video from Adam Savage from NVIDIA, who put together what is CPU versus GPU.
All right, I introduced to you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen,
Leonardo 2.0.
When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9,
8, 7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over. Thank you.
That's the power of GPU, right? Mac has GPU, nobody uses it. Mac has GPU of 500.
Yeah, some 350 cores.
Some 350 cores if we have the recent Mac, but we never use it. So you use the CUDA programming APIs to make use of the GPUs, right? So the GPU takes the financial the numeric calculation in a very parallel processing, because deep learning, one of the examples coming, which I always excited about, is the driverless cars, right? So the driverless cars are deep learning, right? So the car has to move and it has to make the decision what is happening on the street, and it has to keep moving. So the things are happening in real time, 18,000 data points it has to collect, and it has to make the decision, right? So to do that, I think NVIDIA and even Amazon is putting together a big, huge GPU clouds just to take care of these type of deep learning processes. So CPU, while takes care of the rest of the code, and GPU will take care of the compute-intensive code. Simple example, we talk about the images. The training time, when we ran our training time for 64 images, this one came out of NVIDIA, actually. A CPU here is dual 10-core Ivy Bridge CPU is what the CPU is seeing. And GPU is 1 Tesla K40 GPU, actually implemented with a programming language called Caffe. 64 seconds. For 64 images versus 7.5 seconds is basically you see close to 8 or 9 times faster processing if you use the GPU machine again for the deep learning. Now, in day one, what we are using is we are using the first 3 of them, the Theano, Blocks, the Lasange. We use those Python libraries and the languages to do our deep learning. We are currently doing deep learning on a couple of things. One is on the unstructured text and also video coming out of the body cams. So we are using some of those deep learning processes there on the experimental stage. We do quite a bit of machine learning work. Then these are the other tools: PyLearn, Torch, Deep Learning, Caffe, CUDA from CUDA Convent from NVIDIA. They're all very popular languages. So what are the deep learning use cases, right? The use cases are speech recognition. Siri is using it, obviously. Image recognition. We talk all of them already. Natural language processing. Drug discovery and toxicologies, which is lots and lot of data points, then it has to discover it. CRM and e-commerce is kind of making the human behavior analysis, what happens. The driverless cars is actually human behavior analysis. If you go to Google and look for pedestrian detection algorithms, there's a huge study going on because car has to figure it out which direction the human is actually going to move. He's going to cross in front of me or he's going to walk beside of me. Human can do it in nanosecond. How can a driverless car do it? There's a bigger algorithm detections are coming up, and it's basically the human behavior analysis. All of them are video processing, actually. It's video sliced into image into the outcome and the decision making. Going back to unsupervised learning, things have to be unsupervised. You have to keep training it, and it has to keep doing it. Obviously, search and advertising, you all see Google is big in it. These are the companies which are pioneered in deep learning. Even in the olden days, you could call that as artificial intelligence, expert systems. But again, the power of cloud, the power of big data, and the low cost of processing at the low cost is making these fields much, much faster, much, progressive. The universities are using it. Baidu, all the universities and several driverless cars and other people are using it. Facebook, obviously, we know their traces wherever we go. The image recognition is the computer vision. Can you make the computer see who you are, what is there, what is the difference between a mug sitting on a desk versus a human sitting on a desk? All these wearables now, they're going to have this image recognition, which means actually computer vision. Which is happening. So where you're seeing is, again, self-driving cars is one of them. In the retail industries are really looking at the deep learning by looking at the texture of what you're wearing. If you don't have the brand, Polo or whatnot, they can figure it out what kind of texture of the clothes you are wearing and detect that. Obviously, home securities and wearables where you wear the glasses and the glasses have the deep learning. Computer vision / image recognition of what they are seeing, how you make a decision out of that. Shall we take it out from here?
So the other place where deep learning is predominantly used and researched is natural language processing and speech recognition. So in order for the machines to make sense of what we are talking and telling it, it has to understand not just our tone and our meaning, but it has to understand the context in which we are talking to the machines. If you've used Siri or Cortana or the Google Now, which comes with Android, you're using a form of machine learning where you're telling Siri, hey, find me all the restaurants near my current location, right? So before Siri can answer you, it has to make sense of what you're telling it, what you're looking for, by understanding the audio pattern that you're feeding it. And then combine it with your geocentric position and all the information that it can extract from the internet around your geolocation. That's a lot of computation that it has to do. And also, the challenge with speech detection is everybody talks differently. I myself can talk in multiple variations of English. I can do very, very well South Indian accent, and I can confuse my speech recognition application very well. But these systems are also getting very smarter in coming up with ways to mitigate those variations. So this is what I would like to highlight. We are soon moving from a Siri Cortana kind of a domain to a full-blown Iron Man, Tony Stark, Jarvis kind of a domain, where the machines will be able to analyze all the data that's being collected in and around me as a person and interpret my behavior, interpret my likes and dislikes. And it can do that because, think about it, I am wearing an Apple Watch. This watch today collects some statistical information about my heartbeat, pulse rate, my overall activity during the entire day. Likewise, my phone tracks all my movement through the GPS location service that if I have it on. My cars track my data about my driving abilities and how well I drive. It's all collected on cloud. Even the bed I sleep on. These days, you have beds which come with technology which can detect your sleeping patterns and identify any anomalies in your sleeping pattern, right? Now think about all of this data collected about you, around you, every single day. And over a period of time, using deep learning, you would be able to use the machines to analyze and figure out your behavior patterns. Where this is helpful is things like my irregular sleep pattern or my irregular eating habits or my irregular exercise habits. I take it for granted. These are mundane tasks for me. But over a period of time, the machines can flag it as a potential danger to my future health. Because of my irregular sleep patterns now, I might end up with a condition, a medical condition in the future. That kind of analysis the machines can do and flag it and alert me and move me towards preventive medications, move me towards preventive healthcare. A big thing. Rather than being reactive to something that happens to my health, it's good for me to know that, okay, because I've been not sleeping well for the past 2 weeks, in 3 months, I may end up with this condition. I need to make some changes, right? So those are the areas where deep learning can really benefit. Now, it does come with its own caveats because while it sounds nice and fancy, it's not that straightforward because to come up with this kind of analysis, you have to deal with data which is irregular. I may wear this today, may forget my device tomorrow. I may give it to a cousin of mine to wear it for his school and show off. How do you mitigate those discrepancies in the data? That is another challenge which this whole deep learning domain presents and tries to address. Identify the anomalies over a period of time and discard that data as invalid data. Because if I use an incorrect set of data, my analysis and my outcome, my predictions are going to be incorrect. So how do I determine that? Deep learning algorithms can take care of that by observing data and observing behavior patterns over a period of time. So if over a period of 1 month, 2 days, I forget to wear my health device, Fitbit or iWatch, deep learning algorithms will be able to figure out that, okay, there's missing data, and I need to evaluate my assumptions and my calculations accordingly. Finally, I mean, that's my favorite domain, that speech recognition and moving from Siri Cortana to Jarvis. But Chida is very much into driverless cars.
Yeah, just, we have heard enough about the driverless cars. It's pretty exciting, and it's coming up. I think it's going to be reality pretty soon, right? So it uses, these companies uses it, Mercedes, Audi, Google, Baidu, they all researching on that. It uses DNN models. It does real-time pedestrian, which I already talked about. It processes terabytes of data. It has to keep the car moving. So it's not only learning, imagine the connectivity to the cloud while you're driving. If the Wi-Fi fails, what happens? You're dying, right? So, but in addition to the basic functions of braking, stopping, parking, all the other steps have to be taken care of. And beyond that, things have to move, right? So actually, we are thinking of giving a demo, but we have only 10 minutes to go. So we are at day 1, booth number 812. We have a small machine learning demo on unstructured data at booth 812. If you want to stop by, please stop by. And these are all the useful resources which you can go to. We also do a small campaign called Bring Your Own Data. go to the link and give us 50 gig of your unstructured data. We will give you a small machine learning algorithm all the way to the context-sensitive search, which comes out of that your own document sets. Amazon machine learning links are there. Deep learning links based on a lot of NVIDIA, because that's where we took the GPU lessons from. And those are all the discussion from us today. And if you have any questions, please, or we'll be here around. Thank you all for your afternoon. Thank you all for listening us.